Determine the total binding energy in mega electron volts and binding energy per nucleon, also in mega electron volts, of bismuth 209. I wanted to go over this problem because I wanted to take the time to talk about these concepts, some of the concepts at least that are involved in this particular problem. There are some stumbling blocks along the way, and I just want to help you avoid them. So first off, what is binding energy? So when you create a nucleus, or I should say an atom from scratch, you got to bring together all the neutrons and protons and electrons. And in doing so, some of the matter will be turned into energy. That amount of energy is referred to as the binding energy. And the amount of matter that turns into energy is called the mass defect. So in this case, for example, with bismuth 209, I've got to bring together 83 protons, 83 neutrons, and 126 neutrons. And so bringing those all together, some of that matter will be turned into energy. That energy is called the binding energy. Now, mega electron volts. What are those? 1 electron volt is the amount of kinetic energy an electron would have if it accelerated from rest through a potential of 1 volt. Mega electron volts, mega just means 10 to the 6th. So this is just, 10 to the 6th electron volts. The whole reason we use electron volts is because in situations like this, we're going to be talking about small amounts of energy. And so if you're talking about in terms of joules, it'd be on the order of 10 to the negative 13th joules. Okay, 1 electron volt is 1.6022 times 10 to the negative 19th joules. So 1 mega electron volt is, all that times 10 to the negative 13th. So it's small amounts of energy. It's just more convenient to use what essentially are small units. Mega electron volts, these are small units of energy. All right, so how do we go ahead and do this? It starts with this formula for the mass defect. So for bismuth, as I already mentioned, I need to bring together 83 protons and 83 electrons. Okay, well, that's just a hydrogen atom. So it's going to be 83 times the mass of H1 plus, now I have 126 neutrons. So 120. And what I'm doing here is this first part. I'm adding up all the particles that make up bismuth 209. I'm adding up their rest masses. And then I got to subtract the mass of bismuth 209. Now, when we do this, we're going to use atomic mass units because that's what the mass of the atom was that I'm given anyway. It was given to me in atomic mass units, so that's what I'm going to use. So 83 times the mass of hydrogen 1 in atomic mass units, that's, where the heck is it? 1.007825 plus 126 times the mass of the neutron. The neutron mass is 1.008665 minus the mass of bismuth, which is 208.9803987. Okay, so just plug this into my calculator. 1.25 plus 126 times 1.008665 minus 208.9803987. And I get 1.7608663 atomic mass units. So a small amount of matter has been converted. You can see it's not even 1%. It's less than 1% that has been turned into energy. Okay, so that's the mass defect. Now I need to find the binding energy. Okay. So to do that, we've got EB equals MC squared. So I'm just going to go ahead. I'm just using this formula right here. So my mass defect is 1.7608663. I'm going to go ahead and convert it into mega electron volts per c squared. This is a wonderful unit to use, as you'll see in just a minute. And then this, so all this is my mass. I'll just do that. That's the mass defect. And then I'm just multiplying that times c squared. And what's so wonderful here is the c squareds cancel. Makes it very, very simple. So I just take this mass defect that I already calculated, multiply it by 931.5, and I get 1,640.25 mega electron volts. So that's the binding energy. And then I can figure out the binding energy per nucleon. It's per nucleon, so I'm just going to divide by how many nucleons I have. And so that's just going to be this value, 1640.25 divided by 209. And when I do that, I get 7.848 mega electron volts. And there you go.